Hey Honors Physics, this is Mr. Hausman. We're going to take a look at some of the answers to page 15, 18, and we're going to be looking first at springs. Springs are going to be featured, and that means spring potential energy is going to be featured. And the first example is a trampoline, which many of you have been on, very popular for backyard activities. So a lot of people kind of consider or get kind of confused because, if you were to jump up high or maybe jump onto a trampoline, everyone thinks that the resting position of the trampoline, the unstretched trampoline, is the zero height. But if you look back in some of your notes, the way that it works with potential energy of a spring is that your zero is basically the maximum stretch that a trampoline can do, because that's really the lowest position you can be on the trampoline. Remember, so potential energy due to gravity has to have a zero height, and potential energy of a spring is kind of like that distance that you stretch. So let's take a look through here and let's see if we can solve this one. So what we have to realize is that position A is when the jumper, the trampolinist, is at some significant height above the trampoline. So what kind of energy do you have at the highest point? She starts from rest. So maybe she jumped up in a previous jump, and basically you run out of velocity. So let's assume that at position A, the potential energy due to gravity is the only kind. And then when they fall into the trampoline, to the lowest point, of course it turns into kinetic energy in the process, but then it turns back into, at position B, potential energy of a spring, because there is no height left over. And have you ever noticed that when you're in a trampoline, if you were to do slow motion video, you also momentarily come to rest, so you have no motion. So the formula for potential energy due to gravity at A is mgh. The potential energy at the bottom of the trampoline is 1/2 kx squared. And now we put in the mass. Notice the masses can't cancel out because there's no mass over on B side. G is 9.8. Now here becomes the interesting thing. How high is the jumper relative to the zero height? Well, this is the zero, and according to this, that's an 8-meter drop. It's 7 meters until her body hits the trampoline, but then 1 meter of stretching it. But she still has, right? She still has some potential energy when she's at the surface, right? She has some, but then by the time she gets to the bottom, right, she has zero potential energy due to gravity. A little bit more complicated. And the K value is what we don't know. But as you can see, this trampoline, which is probably made of many, many springs, has a stretch displacement of 1 meter, okay? So your K value comes out to be, and that's not a K of a single spring, it's for the entire trampoline, 6,272 newtons per meter. So that's how we tackle the first one, and we think about the different types of energy. Okay, now this is a bouncing mass in the second one. The mass stops here. It compresses here. Now, the spring itself, if it wasn't bouncing, it's an unstretched string, it drops. It falls, and the spring stretches a certain distance. The mass stops at the lowest point. The spring is stretched 0.5 meters. The mass has fallen through a height of also 0.5 meters. So note X equals H. So let's use conservation of energy to find the K of this spring. So what kind of energy do you have at position A? So what you try to do is you basically know that the total mechanical energy at position A has to be equal to the total mechanical energy at position B if there is no external forces, right? No applied force, no tension force. Gravity is considered a conserved force, so it does not affect the total mechanical energy. Well, at A, right, the spring is basically at rest, right? But it's elevated above its lower position, right? And it falls. So at the very top, it has a form of potential energy. That's its rest position, right? and it's unstretched. This is not compressed. This is basically a relaxed spring, neither stretched nor compressed. But it does have potential energy because it could fall. It could turn into kinetic energy. In fact, it does turn into kinetic energy during the fall, but by the time it hits its bottom, it turns into, right, potential energy that's stored in the stretched spring. Okay, so when it's way up at position A, we know that it has potential energy due to height. It becomes potential energy due to a spring. And now let's plug in 0.1 kilograms times 9.8. Now, what height is it? So we don't care what the height is above the ground. We just need to know what is this height above its lowest point. And according to that, the lowest point it goes is 0.5 meters lower. So its total height is 0.5 meters. We don't know the K value, but we do know that it stretches, right? So that spring stretches out 0.5 meters. Don't forget we have to square that. So let's do some math. 0.1 times 9.8 times 0.5 divided by 1/2 or times 2. And then don't forget to divide by 0.5 squared or 0.25. So I get a K value of 3.92 newtons per meter, right? A much smaller spring compared to the previous one. 16 and I believe it. Hey, Honors Physics, this is Mr. Hausman, and this is a preview of some of the problems that you'll be trying in your problem set. This problem is found on page 20, and it is the first time we've seen a problem with total mechanical energy not being conserved all by itself. What I mean by that is there has been a term added that factors in, right, a gain or loss of energy. So each of these problems is a little bit different. The most common force, you may remember that the work is equal to force times distance times cosine theta. The most common force we're going to be looking at is the kinetic friction force, sliding friction, and that will inform a few of the problems that we're trying. Okay, so let's begin. So let's see what this scenario is. Here is a skateboarder. Let's pretend it's maybe Wile E. Coyote. He's going to use the spring to launch himself. And he doesn't go up a hill, he doesn't go down a hill. So let's examine what kind of energy he could have. Well, what you can't tell is that this spring has been compressed some distance, 1.5 meters, and he's at rest. There's no motion here. So maybe there's some kind of braking mechanism, and he's going to launch himself. So fundamentally, he has no motion, so he's got no kinetic energy. He has no gravitational potential energy. So the total mechanical energy at the beginning is 100% or entirely spring potential energy. Later on, at position B, we're going to put an equal sign here, and I'll explain the gap that I just left, is that at position B, he gets launched, he may increase his kinetic energy, but by the time he gets to B, and it doesn't matter what he does between A and B, he clearly has no kinetic energy, because he comes to a rest, he stops at the end of the run. There's no height, so there's no gravitational potential energy, and there's no spring. So what kind of energy does he have? He has no mechanical energy at all. So we're just going to write in as 0 joules. So what happens along the way? Well, the key thing that's happening is that there is an external force on the rider, on the skateboarder. And let's do a quick free body diagram to examine what forces he or she is experiencing. This is a snowboarder, I guess. And of course, they have a weight. The earth pulls them down. There's a normal force because there's a surface that he's snowboarding along and supports you. But as you slide along, you know, I agree that there was a kinetic energy momentarily after A but before B, but we're not asked about that. So during the slide, and it's continuous, there is clearly a friction force. So let's take a look at how that affects that. So we know that if there's a friction force and it's parallel to the motion, then we have a non-conservative form of work. Remember, friction, drag, tension, and applied forces are all considered non-conservative forces. So NC stands for it's a non-conserved form of energy. Okay, so let's start plugging in some equations. We know, whoops, I'm already off to a bad start there. So let's try that again. What's the formula for spring potential energy? 1/2 kx squared. And we've already been introduced to, but we just haven't done as much practice. The formula for work is force times distance. It's a cross product. So we also need to know the angle between the force and the distance or displacement. And that equals 0. And you might be tempted to start plugging in, but I'm going to encourage you to kind of start plugging in more equations rather than putting in constants, such as the k and the x value. Let's do that all in one step a little bit later on. So what force are we talking about? Well, it's the kinetic friction force. And the formula for friction, if you quickly remember, is mu times normal. And the mu is known, but we're going to write out the formula first. Mu times normal times distance. Cosine theta equals 0. So now we've broken it down even further. We've replaced the kinetic friction force with mu normal. Okay, well, let's see if you have your memory on. So how do we find the normal force of that slider? Well, it's equal and opposite to the force of gravity, or mg. So let's just kind of remember that if the force of gravity equals mg, the normal force in this situation, not every situation, is equal to negative force of gravity. So it's the same. It's mg, but it's positive now. So let's rewrite this one more time, showing every possible substitution. So what did we just say a minute ago? Normal is equal to force of gravity, which is equal to m times a positive g. We'll put a little dot there to remember it's positive g, times distance, times cosine theta. Finally, we have everything we need to solve for the distance. How long along the ground does the person slide before they lose their kinetic energy or all of their mechanical energy? So let's do it. Let's do it up. 1/2 of 4,000 times 1.5 meters squared plus 0.3 times a 60 kilogram mass times 9.8 times d times cosine, and let's examine the angle. Well, the motion is clearly moving forward. You're sliding forward, so it's going to the right. It's not really a two-directional arrow. That's kind of a mistake. And the force is against you, so we're dealing with one of those situations where we have a cosine of 180 or -1. So if you take your time and your calculator and you simplify this, you're going to find out that there's 4,500 joules of potential energy. And we can simplify much of this, but not all of it. 0.3 times 60 times 9.8 times cosine of 180, that's -1. And you find out you have a -176.4 times d. And you're setting that equal to 0. So what that's really going to do is it's going to set up a -176.4 times d equals -4,500 joules. And you might be thinking, I thought energy was never negative. It only becomes negative in the mathematical context, right, of moving to the other side of the equation. We subtract it from both sides. And in the end, we're going to get a positive distance of 4,500 divided by 176.4. And you find out that your distance is 25.5 meters. It would take 25.5 meters to slow that person down. We're going to do one more, and I know it makes the video a little longer. Hopefully you're watching the parts you need. So let's kind of zoom in here, and let's do another one. This time, we'll explain a few fewer of the steps. So at top of the hill, we have some height, we have some velocity, so we have potential energy, and we have some kinetic energy. Bottom of the hill at B, we've got kinetic, but clearly it's implied for this flat part, the 12 meters, we also have a force that is causing some work to be done. And I bet you can already anticipate it's negative work because friction is against you. So we've got mgh plus 1/2 mv squared plus force of kinetic friction times distance times cosine. And you might be tempted to plug in, but I think we actually need to do some simplifying or some substitution here so that we can actually plug in more. So let's keep going. mgh plus 1/2 mv squared plus mu times normal. But I already remember from my previous problem that the normal on a flat region, right, when he gets down to here, won't his normal force be opposite his force of gravity again? They're directly opposite. So I can do mu mg. The distance is known this time, and cosine of 180 degrees. And we're trying to find VB. So I think that's our final step before we start plugging in. So before you do that, I hope you might have spotted that there is mass in every single term on the left and on the right. So we really just need to do 9.8 times a height of 9 meters plus 1/2 of 9 meters squared over second squared. I've already squared the 3. And now we have a mu, a coefficient of kinetic friction of 0.6 times 9.8 times a distance of 12 meters times -1 equals 1/2 VB squared. So now that left side is just very busy, but we just have to tackle it all. 9.8 times 9, 88.2, plus 1/2 of 9, 4.5, plus 0.6 times 9.8 times 12 times -1, negative 70.56 equals 1/2 of VB squared. Your VB, I think we can do this all on our calculator, 88.2 plus 4.5 minus 7.56. Divide that by 0.5. Take the square root to get my V from my VB squared. And I get a V of 6.7 meters per second, 6.654, if you want to check. And that's possible. Does it make sense? Well, you definitely went down the bottom of the hill, so your velocity should go up. But as it turns out, this velocity is limited by the energy that was stolen on the flat part, right? Friction steals your energy, in this case, does negative work, and the net result is a velocity that is faster than 3, but not as fast as it could be.